Hello my dear children, hope you all are fine over there. Once again welcome to our physics class. Children, in our previous chapter we had discussed wave optics and we have completed that session wave optics. Today we are going to discuss our new chapter, chapter 14, semiconductors. So what do you know about semiconductors? Semiconductors are those materials whose conductivity lies between conductors and that of insulators. Children, people were always interested in the controlled flow of electric current. Huge amount of current is flowing through a circuit will damage that circuit. Hence, controlled flow is preferred. Earlier, valves were used for this purpose, which was the only device known at that time which provide the unidirectional flow of current. But later, when semiconductors were gradually introduced and when their properties were studied, it was found that semiconductors are more advantageous than valves. Also, valves have got some demerits like it is bulky and it consumes more power, it has limited life, and also it always works or operates at high operating voltage. But at the same time, semiconductors will overcome all these demerits. Semiconductors are very small in size, very compact, consumes low power, and it has long life. Also, it has low output voltage. And you might be well aware of the difference between the older television and the new LCDs and LEDs. Okay, the size is very compact because it is made up of semiconductors. Also, semiconductors has many applications in the medical field, communication field, defense. Okay, children. So, on the basis of conductivity, materials are classified into metals, semiconductors, and insulators. So, the conductivity of a material indicates whether they can be classified as metals, semiconductors, or insulators. Metals are those materials that have high conductivity and low resistivity. Example, sodium, lithium, potassium. Okay, all are metals, they have high conductivity. And semiconductors are those materials that have conductivity and resistivity in between metals and insulators. Example, germanium, silicon. Germanium, silicon are the commonly used semiconductors. Then insulators are those materials that have high resistivity and hence low conductivity. Example, glass, wood, paper, rubber, etc. Now, we can also classify materials on the basis of energy bands. So, what do you mean by energy band? In order to explain the energy band, consider a lithium metal sheet or any metal sheet. So, here I am considering a lithium metal sheet, lithium metal. And a lithium metal sheet consists of many lithium atoms, and all these atoms will be closely spaced like this, isn't it? So all this represents lithium atoms and this dot represents nucleus. And around the nucleus there will be orbitals, inner orbitals like this. And these are the outer shells, okay, outer orbitals. And you can see the outer orbitals of the adjacent lithium atoms are overlapped, isn't it? So due to this overlapping, the valence electrons will be affected more than the core electrons. Okay, and this overlapping gives rise to a large number of closely spaced energy levels like this. And this set of closely spaced energy levels forms a band, and this band is known as energy band. The energy levels in which valence electrons are present is known as valence band. Beyond valence shells, many shells are there, but it is empty. And these energy levels are called conduction band. Okay, and this will be the energy band diagram, where on the ground level you have the valence band, and above the valence band you have the conduction band. You can see the conduction band. And there is this gap between the valence band and the conduction band, and this energy gap or this energy difference between valence band and conduction band is called energy gap, which is denoted by Eg. Okay, usually electrons will be present in the valence band. When these electrons absorb energy and get excited, they will jump to the conduction band, which is responsible for the conduction. Only when the electrons are available in the conduction band, conductivity occurs. Okay, so this is about energy bands and how can we explain the conductivity of metals, insulators and semiconductors on the basis of this energy bands. Let's explain that. See, classification on the basis of energy bands. In the case of conductors or metals, the conduction band and the valence band partly overlap each other and there is no forbidden energy band gap in between. You can see this figure. In this figure you can see conduction band and valence band are overlapped. So the electrons in the valence band are easily available in the conduction band. See, the electrons from the valence band can easily move into the conduction band. Hence, large number of electrons are available for conduction. The resistance of such materials is low and conductivity is high. Then about insulators. In the case of insulators, a large energy gap exists between the valence band and the conduction band. The energy gap is so high that the electrons from the valence band cannot move to the conduction band by thermal excitation. Here you can see the valence band and conduction band are separated by a large energy gap. So the electrons cannot jump to the conduction band. Hence, there is no electrons in the conduction band. So there won't be electrical conduction. Electrical conduction is not possible. And what about semiconductors? In semiconductors, a finite but a small energy gap exists between the valence band and the conduction band. At room temperature, some of the electrons from the valence band acquire energy and move into the conduction band. But at high temperature, semiconductors have high conductivity because at high temperature, more and more electrons acquire energy and move into the conduction band. So, conductivity will increase at high temperature and resistance is also not as high as insulators. So, this is the energy band diagram for semiconductors. Here the valence band and conduction band are separated by a small energy gap. So whenever external energy is applied, electrons from the valence band acquire energy and jump to the conduction band and conductivity occurs. So that's why semiconductors, the conductivity of semiconductors lies between that of conductors and insulators. Now we can discuss more about semiconductors. There are two types of semiconductors. The first one is intrinsic semiconductor and the second one is extrinsic semiconductor. So what do you mean by intrinsic and extrinsic? Let's first discuss about the intrinsic semiconductor. Intrinsic semiconductor is the pure semiconductor. It will be free from impurities. The electrical conductivity of this intrinsic or pure semiconductor is called intrinsic conductivity. Okay, so intrinsic semiconductor is the pure form of semiconductor and we will not add any other elements or atoms inside this intrinsic semiconductor. So it will be free from impurities and its electrical conductivity is its electrical conductivity is known as intrinsic semiconductivity. Okay. Now, can you see a figure on the screen? This figure represents the crystal structure of silicon or germanium semiconductor. I told you silicon germanium atoms are commonly used as semiconductor materials. Okay, so this crystal structure represents the silicon or germanium crystal structure, and +4 indicates this semiconductors have 4 valence electrons in their valence shell. And you know, in order to obtain a stable configuration, they need 8 electrons in their valence shell. So they decides, this silicon and germanium atom decide to share their valence electrons with their neighboring atoms, so that each of this silicon or germanium atom can obtain 8 electrons in their valence shell. If you consider this germanium atom as an example, suppose this is the germanium atom that we are considering, and this germanium atom has 4 valence electrons, 1, 2, 3, 4. Okay, now in order to obtain a stable configuration, this atom shares its electrons with this neighboring atom this neighboring atom, this atom and this atom. So what happens? On this side, this germanium atom has 2 electrons now because it has shared its electrons with each other. So both of this germanium atoms has 2 electrons now. So 2 electron, again here it has 2 electrons, so 2 plus 2 4. Here it has 2 electron, 4 plus 2 6, and here again it has 2 electron, 6 plus 2 8. Now this germanium atom has got 8 electrons. Similar is the case of all atoms here on this crystal structure. So they acquire a stable configuration through the sharing of electrons, and hence a bond is formed between each of these atoms, and this bond is known as covalent bond, and covalent bond is the bond formed by the sharing of electrons. You already know that concept. Okay, and here you can see no free electrons are available in the crystal structure, isn't it? All the electrons are bonded by covalent bonds. You can't find any free electron which are free to move through this crystal structure. So, in order to increase the conductivity of intrinsic semiconductor, we must supply an external energy to this crystal structure. So, whenever an external energy in the form of heat is supplied to this crystal structure, this covalent bond will break. When the covalent bond breaks, electrons will be free, and that free electrons will conduct, isn't it? So when this bond breaks, the electrons will become available for conduction, and this bond can be broken by supplying or by giving an external thermal energy. When the bond breaks, what happens? Suppose this bond breaks. So when this bond breaks, this electron will become free. So it is free to move through the crystal lattice, and it will move and it will conduct the current. At the same time, a problem is created. When the electron moves from this position, a vacancy is created here, and this vacancy is known as Hall. Hall is the vacancy created by the electron. Okay, and since this Hall represents the deficiency of electron, this Hall is assumed to have a positive charge. So Hall is actually a site. It's a vacancy created by the electron, and that Hall has a positive charge because it is the deficiency of electron. Now as soon as this electron finds a positive charge here, it will be attracted to this positive space. So electron will jump from its position to the positive space. Again here a vacancy of electron is created. So now Hall is here. Again this Hall has positive charge. As soon as this electron finds a positive charge here, it will be attracted to this positive space. Again a positive space or Hall is created here. So whenever this electron finds this positive charge, it will be attracted to this positive space. So you can see the movement of electrons from Hall to Hall, and we feel that halls are actually moving from one place to another place inside the semiconductor. But halls are not charged particles. Halls are just vacancies created by the electrons, and the electrons move from one hall to another hall. So we feel that halls are moving inside the semiconductor crystal from one point to another point. So here two types of movement can be observed. One, the movement of the free electrons, which is available due to the breaking of that covalent bonds, and another is the movement of electrons from hall to hall. So due to these two types of movement of electrons, two types of currents can be observed, because you know whenever electrons move through the conductor or any crystal, current is generated. So here two types of electron movements can be observed, due to which two types of currents can be observed. And one is the current generated due to the movement of free electrons, that can be considered as electron current, and another due to the movement of the electrons from hall to hall, and that is considered as the hall current. So the total current inside the intrinsic semiconductor is the sum of electron current and hall current, IE plus IH. Also here the number of electrons is equal to number of halls. and these electrons are and holes are the charge carriers, because these materials are responsible to carry charge inside the intrinsic semiconductor, and this will be equal to the intrinsic carrier concentration. Okay, so the total current in the intrinsic semiconductor will be equal to the sum of electron current and hole current. Okay children, so this is about the intrinsic semiconductor, and we can explain the same thing using the energy band diagram of intrinsic semiconductor. See, this is the energy band diagram. This figure represents the situation at 0 Kelvin. When the temperature is 0 Kelvin, you can see no electrons are available in the conduction band. Conduction band is empty and valence band is full. That means all the electrons are present in the valence band when the temperature is 0 Kelvin. So no conductivity occurs in this situation. This intrinsic semiconductor behaves like an insulator now. Now, when external energy is supplied to the semiconductor, some of the electrons inside the valence band acquire energy and move to the conduction band. So here you can see 6 electrons has reached the conduction band. That means 6 vacancies are created in the valence band, or 6 holes are created in the valence band, and we feel that holes move within the valence band and electrons moves within the conduction band. The energy gap between the valence band and conduction band is small, because it is a semiconductor. So electrons can easily jump or cross this energy gap and reach the conduction band. So thus we can explain the conductivity of intrinsic semiconductor on the basis of this energy band diagram. Okay, so that's all about intrinsic semiconductor. So it is the purest form of semiconductor. No impurities are added in that semiconductor, and its conductivity is known as intrinsic conductivity. At 0 Kelvin, intrinsic semiconductor is an insulator, but when the temperature is increased, it behaves like a conductor. Okay, so that is the peculiarity of intrinsic semiconductor. Next we can discuss about extrinsic semiconductor.